David Gadia, and he's going to be presenting stereoscopy-based procedural generation of virtual environments. David has received his Master's of Science and PhD in Computer Science from the University of Milan.
Okay, thank you, Chris, and hello, everyone. What I'm presenting today is an application of stereoscopic parameters inside computer graphics, in particular in a particular field of computer graphics, which is procedural modeling and procedural generation of virtual scenes. You may have seen some of examples of procedural generation in the 3D theater on Monday, and it's something that is more and more used in movies and video games. The generation of a lot of models, trees, buildings, in automatic or semi-automatic way. These scenes are often visualized in 3D. The point is that often, to my knowledge at least, the stereoscopic parameters are not used as a direct parameter to generate the models inside the scene. So what I propose in this paper is to use, to generate a scene using stereoscopy since the beginning of the creation of the scene. We can go back to the comment Neil Doxon has done on last Monday, the use of stereoscopy to create something creative tools for creative stereoscopy. And to do that, we need the tools to accurately done to allow the designer of a stereoscopic scene to use all the settings since the beginning. Just to give a small brief introduction to procedural modeling, the procedural modeling is based on some equations, some set of rules applied to basic shapes in order to create automatically a complex scene without having to model manually all the features in the scene. For example, very common examples, fractals, used to create some images or fractal terrains. L systems, in which using some parameters and a set of rules, you can create complex shapes like trees. And more recently, in more complex systems, the procedural creation of cities. This is a work from 2001, based on the use of some images, giving some information regarding the elevation of the field, the population density, the presence of sea or lakes. It can generate a set of streets, and on these streets you can, using different rules, generate a different kind of buildings and creating something like this. Now, in this paper, I try to consider the creation of some of these kind of scenes using stereo parameters to rule the creation of the geometry. The idea is to create a more effective and more pleasant stereoscopic scenes using the stereoscopic parameters since the beginning of the production stages. I present two simple examples of integration of stereoscopic parameters in a procedural pipeline of a computer graphics production software. The first is very simple. The automatic geometry filling of the stereoscopic camera frustum. And the second one is the automatic detection of window violations and the application of the floating window. We have decided not to develop a system by scratch, but rather to consider the integration of these techniques inside some already available tool, opening also the discussion of what is provided from the production by the production tools when we talk about stereoscopy. Now, searching, there are two sets of production tools. One very specific, like the city engine, specific for creation of cities, but they often do not provide stereoscopy. Or considering a general purpose tools, we more or less go with ID&A, which is a full production tool based on procedural generation. It provides a stereoscopy, but the problem is that not all the parameters of the stereoscopic setup are provided as tool inside the node-based generation of the scenes. So you can set a stereoscopic camera, you can produce a stereoscopic image, but you cannot use the parameters of the stereoscopic setup in the production of the scene. So we have opted for a different approach. We have considered the Blender, which is open source. It provides a stereoscopic pipeline. It is not natively a procedural tool, but by use of this add-on, Sverchok, from a Russian developer, it is possible to extend the node editor of Blender that is already present for creating material for compositor, to use it as in ID&A to create a geometry. In this case, we have the maximum flexibility. We have all the source code of Blender. We can do whatever we want. We can check every step of operation done inside in Blender. Obviously, this is particularly true for Sverchok. Sverchok is heavily in development stage, so you may lose stability when the development goes on and new versions are available. But just to break the ice with the topic and to do some preliminary tests, we found it a better solution. Test scene. We have decided to build a very simple city, not as complex as in the previous work, both because we didn't have enough computational power. We are talking about hundreds of thousands of triangles in the scene. So we have, now it's quite dark and, actually, but we have decided for a very simple rendering level because the techniques that we are proposing are independent of how much you push in the rendering. You can do it in toon shading, photorealistic rendering. We are discussing about the creation of the geometry. So at the moment, we have decided to stay with an acceptable range of rendering. These techniques also can be integrated with other kind of scenes, trees instead of buildings, particle systems. They don't matter. We are talking about the stereoscopic parameters and how we can use it. So I will not go into the details of the construction of the geometry because it's not the topic of the paper, but simply we start with a patch. We subdivide it with some scheme ruled by some parameters, in this case some sort of diamond-based shape to build streets and lots. And then for each lot, we calculated the height of the buildings, mainly randomly, but there are some parameters that the user can set. And with many blocks, you can create a city. You can also select some blocks to be some sort of downtown with the skyscrapers, with the other heights going down in with Gaussian way. But again, no more details. Let's go to the stereoscopic setup. First one is almost trivial. I was sure to find someone else I've considered it, but I've not found paper on it. Maybe the production tools used in the production companies that are not publicly available, they maybe use this since years, but nobody has discussed about it. It's trivial. If I have to create a 3D computer graphics, I have to decide the 3D position of an object in a scene. So let's use what is called in computer graphics camera space. Let's decide the position using the camera as the origin of the world, and let's decide the depth, the Z position of the objects, considering the stereoscopic frustum. In order to have control of the final depth range of the scene, having the control of the final parallax on the screen, and using only one parameter, you can also re-edit the scene in case the material must be edited or converted for other setups or other possible solution. So the idea is to introduce a rule like this, to decide the depth, the z coordinate of the geometry inside the stereoscopic frustum, limiting in a set where the minimum z can be the near plane of the camera or something, some other value decided by the user. And the maximum is given by this, where this one is the distance from the camera to the maximum parallax plane. And I can calculate it because it's based on the FOV of the camera, the convergence, the distance of the convergence plane, the size of the sensor, so you can go to the magnification factor, the size of the final image on the screen. All these parameters are known in a computer graphics setup. So I can calculate what will be the maximum parallax on screen and where is the maximum distance leading to the maximum parallax plane. And with these simple parameters ranging from 0 to 1, I can fill it. So from top, you see I've stopped at 0.5. You can see as a percentage, 50%, 80%, 95%. It's quite simple and straightforward. But here, before showing you some example, the problems. Blender, but also the other tools providing stereoscopic software, stereoscopic setup, I'm sorry, they give you the tools. They let you set the interaxial distance. They let you set the convergence plane. They provide you a visualization of the stereoscopic frustum of the planes in order to manually place the objects inside the frustum. But they don't give you back the values. There are no panels on the graphic interface telling you, OK, the maximum parallax plane is that far. If it's equal to the far plane of the camera, OK, you're lucky. But otherwise, you have no way to know where it is, nor in the API, if you want to develop a script, it's provided. So it's calculated inside the software, but they are not provided from the user. So you cannot use it since the beginning. So in this case, rather than modifying the whole code of Blender, that is something that can be done when it's needed, because you have also to contact the developer of Blender, and there is some policy. We had to develop a Python script to recalculate the position of the maximum parallax plane in order to have it available to use it in the generation. So we have to do something that is already calculated inside Blender, but is not provided from the software. Having done this, you can use it and you can apply the value in your generation script to create the geometry. So the problem is the production software do not provide a full consideration of the stereoscopic setup in all the stages of the production. And this is something that we may discuss on. So we have to switch to 3D, glasses on. There are just free, yeah, thank you. There are just free image, but then I have some other results on the hand. Everything. Okay, this is maybe we may have to switch the lights off, I'm sorry. This is our scene with a SFF parameter of 0.5. Now, if you see on the background now, I don't know if it has switched. OK, now probably. Now it's 0.80. And OK, 0.95, so almost filling the volume. So with just one parameter, I can control the automatic creation of this. In this scene, we have 2,700 of buildings and something like 170,000 of triangles. So all created procedurally, and the depth range controlled by these parameters. There are some window violations. I don't know if they are noticeable, but we will address it in the second technique. So we can go back to the 2D. Keep your glasses on. You keep your glasses near to you because we have other results in hand. Okay, so this was very simple. Second one, a bit more sophisticated. We have created a scene procedurally. In this scene, it may happen that we have window violations because some objects may be placed in the negative retinal river areas. So the idea was to detect automatically these violations and to automatically place the lateral mask of the floating window technique as actual 3D objects inside the scene, occluding the geometry producing the violations. This technique has 4 steps. You already know how it works, the floating window principle. If we have an object in a retinal rivalry, negative retinal rivalry, we think to have the window tilted like this in order to introduce a mask in the final scene. Usually, the most common way to do it in post-processing, applying the lateral mask on the final image. We are considering to apply it in 3D. Again, our approach is based on some operation, Boolean operation between the geometry of the scene and the frustum of the stereo camera. Again, same problem as before. The frustum of the camera, the stereoscopic camera, is shown as a visual aid, but there is no way to assess it as an actual 3D model to use in the scene. So we had, again, to implement a Blender script, Python script in Blender, to recalculate the values of the planes, of the vertices of the planes building the camera frustum, to use these vertices to create an actual 3D model to add in the graph of the scene, in order to use it for our purposes. Again, all this calculation is already done in Blender, but is not provided you if not like a visual aid, a visualization of where to place objects in order to have an idea of what will be the final depth. It's not very complicated because we know the FOV, we know where is the distance of the convergence plane, we have calculated where is the maximum parallax plane, so it's just some trigonometry and something more just to find the vertices. Having done this, we can calculate, can have actual models. In this case, considering that we are doing a detection of window violations, we are interested in these 2 solids, the 2 negative parallax frustums that are represented here. Let's go fast. Top view, you do it in the both sides. We have the model. You do a Boolean operation between the model and the solid of the retinal negative frustum. And you detect this one. And in particular, we need this point because we have to place the mask here, and this vertex does not exist. So now you have the point. You find it simply doing a depth rendering pass in order to have a depth image, depth buffer. You search for the minimum one. It's trivial if you have a triangle. It's not trivial if you have thousands and thousands of triangles. Once you have this, you create an actual plane, black plane in the scene, 8 like all the field. In the beginning, you could create it as large as you want. And then you do another Boolean intersection between the frustum and the plane. And what you have is a patch in 3D placed in front of the geometry that occludes exactly the geometry behind. This is a visualization in 3D of what is the result. And maybe I will switch only to the final video, not to the image. Sorry, I'm running very late. Not sure I will provoke the same enthusiastic reaction of the audience shown there. The idea was, this is the image of 0995 without And with maybe with, I don't know if it's with the lights, the floating window is not so dark. Again, another view. And again, with the floating window, automatically applied. And finally, this is a 20 seconds movie of our scene, created with a floating window procedurally generated in each frame at the correct size. So again, less than 3,000 of buildings and 170 triangles created procedurally. Obviously, you can create everything you want, maybe applying the same techniques. Very final remarks. The techniques are promising. You can do whatever you want once you have the tools. If you have the tools since the beginning, you can do whatever you want. If you don't have a better integration of stereoscopy inside the production pipeline, you will be limited. In case of an open source tool, you can apply the modification, you can communicate with the community developing the tools. In case of a proprietary production tools, there is the need of some discussion and collaboration with the developers. Thank you for your attention. I was just finishing with the joke.
Okay.